So that's chapter 3, guys. And a probability experiment is an action or a trial through which specific results, counts, measurements, or responses are obtained. I'll give you an example right away. Roll a die, guys. This is an experiment. That's a trial. What are the outcomes of the rolling a die? The die has 6 faces. So you guys, would you agree with me if I tell you the outcomes could be, we get 1 face up, 2 or 3 or 4 or 5 or 6. This is an probability experiment. We're just rolling a die. An outcome is the result of a single trial. So when I said you would get 1, 2, 3, 4, 5, 6, each one of them is called an outcome. We don't know what the outcome is. I'm rolling a die. You don't know whether it's going to land on 1 face up or face 2, but you know it's one of those 6. The sample space, guys, is the collection of all the outcomes. So if I roll a die and I want to write the sample space, it will be either a 1 or 2 or 3 or 4 or 5 or 6. If we toss a quarter, guys, you get 2 outcomes, either a head or a tail. So the sample space will be head, comma, tail, just 2 events. What is an event? An event consists of 1 or more outcomes and is a subset of the sample space. And let's give you an example, which is a roll a die. You would win if you get a 3. Do you guys know what would be your chance of winning?
1 out of 6.
1 out of 6, because 3 is a winning number and there is only 1 3 out of 6 faces. It is 1 out of 6. So here you go, guys. You already defined, you know what the probability is. The sample space, guys, will be 1, 2, 3, 4, 5, 6. These are all the outcomes that you have no control of. You cannot control which one is going to show up or going to be face up. But all you know that it's going to be one of those 6, unless if the die is not a fair die, it's a loaded die, then you could get different results there. You would win if you get an even number on the die. So your chances of winning will be either if you get a 2 or a 4 or a 6, because 2 is even, 4 is even, and 6 is even. So these are examples of a probability experiment. Here's another example, guys. We're going to roll a die and toss a coin. Describe the sample space. So can you guys tell me, if you do those 2 together, what would you get as an outcome? What were the possible outcomes? Can we list them? So we have a die and a coin. Okay, what are the possibilities when you roll, just a die and toss a coin? What is it possible that you see? Can you help me list them? You could get 1 face up on the die and you can get a head. Or you could get a 1 and what, guys? A tail.
Tails.
Or it could be 2 and a head and 2 with the tail. 3 with the head, 3 with the tail. You have no control of that, guys. You're just rolling and then you don't know what's going to happen. Can you count the outcomes for me, guys? How many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 outcomes. So your sample space is all of those. You just put it like that, 20 braces. That's your sample space. Now, you would win. Let's say you're playing a game. You would win if you get a 1 and a head. What's your chance of winning, guys?
1 out of 12.
1 out of 12, exactly, because there's only one outcome that has 1 in a head, and I have a 12 of them. You would win if you get a 6 and a tail. Your chance of winning, guys, will be only 1 out of 12 because there's only 6 in a tail. There, just 1 6 in a tail out of 12 outcomes. All right. If I roll 2 dice, guys, 1 dice and another one, how many outcomes are there? Remember, a die has 6 faces. If you do them together, something like that, how many outcomes can you count as a result of the experiments? What are the possible outcomes?
12.
Okay, I had a 12. Anyone gonna go higher than 12? I would say it's more than 12.
24.
Right?
Is it like 64?
That's too much. So 12
24.
is too low. That's 1 die, and that's the other one.
36.
36 is the perfect number, and I can convince you guys why it is 36. I know that students who said 12 thought of it 6 and 6, 12, they're together, but it's a lot more than that. And let me tell you why. You could get a 1 on the first die and a 1 on the second, a 1 on the first and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. Then you could get 2 and a 1, 2 and a 2, 2 and a 3, and then until 2 and a 6. And then, guys, 6 and a 1, 6 and a 2, 6 and a 3, etc. 6 to 6. You're gonna get 6 on the first one, 6 on the second one. It's 36. But guys, you don't need really to list them to figure out how many. I'm gonna show you a very easy way to figure out how many outcomes you should have. It should be 36, and let me tell you how we do figure this out. Instead of adding 6 and 6, what should you have done, guys?
Multiply.
Multiply, and then it is 36. And to prove my point, guys, let me show you here in the example before. We have a die, which is 6. We have a coin, which is 2. If you do the magic of multiplying, guys, what is 6 times 2? 12. And look, the 12 is standing right there. You don't even need to list them, guys, to figure out how many outcomes. You just multiply the events. How many times the first event can happen, how many times the second event can happen, you just multiply the two. 6 times 6. So if you guys toss 3 dimes, how many outcomes are there? Each dime has 2 outcomes, remember. So when you're doing it, there are 3 of them. So how many would that be?
8.
8, and I do agree. 2, 2, 2. And you guys, just to prove this to you, I'm gonna list them for you. And there is no way, impossible for you to come up with more than 8 or less than 8. Let's list them. We could get head, head, head. We could get head, head, tail. We could get head, tail, head. And there is one more. We could get head, tail, tail. Or it could be tail, 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 head, tail, head, tail, and tail, what? Head, head. It is impossible for you guys to come up with any arrangements other than those 8. Because the rule says, if you know that this can happen 2 times and this can happen 2 times and the third one can happen 2 times, all 3 together will happen 2 times 2 times 2, 8 times. That is the rule. So it's 2 times 2 times 2, 8. No need to list them, but just to show you that I was able to list them. So here is what I'm talking about, guys. If one event can occur in m ways, And a second event can occur in n ways. The two events together can occur in m times n. No addition, guys. It's multiplication. You just multiply. And let's give you an example on this. You purchase a car. You have the possible manufacturers, car sizes and colors are listed. You could buy a Ford, GM, or Honda, different manufacturer. You have a choice of compact and mid-size, and you have a choice of white, red, black, and green. How many different ways can you select? One manufacturer, one car size, and one color. So 3 events at the same time. Can you guys give me the answer? So in how many ways you can select a car that could be from any manufacturer, any car size, and any color? How many manufacturers do we have, guys? We have 3. And how many sizes we have? We have 2. And how many colors we have available? We have 4. And what is the operation that I'm going to put in between? Multiplication, guys. You have 24 choices. And the answer is 24. You don't need to list them. And this is called the fundamental counting principle. One event can happen m times, another one happens n times. The 2 events together will happen m times n times. And here we're asking for the 3 together, and that's why we took count of the first the possibilities of the manufacturer, possibilities of the car size. There's only 2 of them, guys, and then the 4 here. Okay. Definition of probability. Here's the classical definition of probability. It's number of outcomes in your favor number of possible outcomes, all possible outcomes. And this is the definition of probability. Favorable outcomes, that the outcomes that would make you win. Possible outcomes, all of them. How many? Like, for example, here is 24. That's the total number of all outcomes, 24 of them. So let's do an example, guys, and to understand how to compute the probability. You roll a 6-sided die. What's the probability of rolling a 3, guys? Can you tell me what's the probability of rolling a 3?
1.
3
1
times
out
6.
of 6. So there is one outcome in your favor, which is the numerator, and the ones that you can't control any of them. There are 6 actually could show up. So 6 different outcomes. So I do agree. And here's how we write the probability, guys. We do probability. We call the event A. We just put the capital letter A and we put 1 out of 6. What's the event B? Rolling a 7. Who can tell me what's the probability of rolling a 7 on a die? Don't play this. You'll be losing if you play that 7.
Isn't that impossible?
Yes. So what's the probability if it is impossible?
0.
0. There is no 7, guys. So actually probability of B. There are 6 possible outcomes, but 0 in your favor because none of them is going to be a 7. So exactly, when the probability is 0, that's an impossible event. What's the probability that today is Friday? It's 0. It's not a Friday, so that's an impossible event. Okay, what's the probability of rolling a number less than 5? You guys can safely put a 6 always in the denominator because that's the total number of all possible outcomes.
So less
Okay.
than 5 would be 4.
Would be 4, because what are the numbers that are less than 5? There's a 4, there's a 3, there is a 2, and there is what? The 1. So there are 4 of them. And the answer is 4 out of 6. I don't care, guys, about the actual values. All I care about the count, how many. Here I know less than 5, I could have a 2, 1, a 2, a 3, a 4. All I need, just count them, guys, 4 of them. We don't count 5 because he says less than 5. So the answer is 4 out of 6. All right. Another definition of probability. Let me just give you one more definition example, just to have you have a good grasp of it. Roll 2 dice. You would win, guys, probably $50 if you get a sum of 11 on both dice. What's the probability of winning? So you pay $5, you win $50 if you get an 11 face up. You add the 2 faces, you get 11. What are your chances of winning? First of all, can you guys tell me what's going to go in the denominator? That should be an easy one. We decided when we have 2 dice, how many outcomes are there?
12.
Not 12. We didn't say 12.
36.
36. We said 6 times 6, 36. I counted them. So it is 36. Okay. Now, guys, how many outcomes would work on your favor? We'll give you a sum of 11. So what should show up on the die face up in order to give you an 11? Give me the possibilities, guys.
5 and 6.
5 and 6, that's one. There is more.
6 and 5.
6 and 5, that's another one. Anything else? That's it, huh?
8 and 3.
There is no 8 on the die.
Nothing else.
Yeah, that's it. So 2 out of 36. That's your chance of winning. You would win, guys, if you get a sum of 9. Let's figure out the probability. So feel safe, guys, to put 36 at the bottom. Now give me all the combinations that will give you a sum of 9. Let's list them.
6 and 3.
6 and 3, that's one. And you don't count them as 2, guys. It's a pair because you're doing 2 actions at the same time. Two dice. That's a 1.
3 and 6.
3 and 6. That's another one.
5 and 4.
That's another one.
And 4 and 5.
That's another one. And I know our students might say 7 and 2. Remember, there is no 7 on the die. So it's 4 out of 36.
Yes.
That's a better, higher probability than this one. So if I am to play a game, I would prefer to play this one rather than playing that one because I have a better chance right here. Okay, last one, probability of sum of 3. Again, guys, that's a 36 at the bottom. What would you get on the 2 dice to get a sum of 3? What should you get?
1 and 2 and 2 and 1.
That's it.
Yeah.
2 out of 36. And that is the definition of classical probability. Let's give you a definition of statistical probability. If you have a table like this, how would you find the probability? It's just the same as a relative frequency that you learned when we did frequency distribution table. So it's sum of all frequencies and the frequency of the event. And it's easier explain this in an example, using an example. Let's show you guys. This is another definition of probability. It's pretty much like the classical, but using tables. A company is conducting a telephone survey of randomly selected individuals to get their overall impressions of the past decade. So far, 1504 people have been surveyed. These are the total, guys. Look, sum of all frequencies. What is the probability that the next person surveyed has a positive overall impression? So probability of positive impression. According to this definition, it says, first of all, give me the total. which is 1504. What do you think should go in the numerator? It says the frequency of the event. And what's my event here? Positive impression. How many people said that they have a positive impression here?
406.
406. And that would be your answer, guys. A probability can never exceed 1, guys. It's always between 0 and 1. Don't flip the numerator and the denominator, otherwise you'll get an answer over 1. That's impossible. Cannot have a probability that exceeds 1. So it's 406, 1504. I might give you this question on the test and ask you what's the probability of a negative impression. What would be your answer?
752 over 1504.
Exactly. Or the probability of neither negative nor positive, it will be 316 divided by 1504. It's a relative frequency, guys. That's exactly like what you learned for relative frequency. And when you do an experiment, guys, a large number of times, the classical definition and the empirical definitions will be pretty much the same. It's the same definition of probability. Now, one time I asked my students and I told them, what's the probability of tossing, just a coin, just and landing on a head? And they said 50-50. Do you guys agree with that? It's 50% head and 50% tail, correct? But what about if I start, just tossing, just a dime right now? And you notice that you're seeing a lot more heads, just at the very beginning than tails. Would you still be convinced that it is a 50-50 chance? What do you think? I could do it, guys, right now and start tossing, just a dime and showing you, just more heads than tails. Would that change, just your understanding that the chance is 50-50? What would you say?
No.
It wouldn't, but how can you convince? How can I convince you it's 50-50? I do it the first time, it's heads. The second time is heads. The third time is heads. The fourth time is tails. Fifth time is heads. Well, you're seeing more heads than tails. You're getting confused. But I can convince you that it is 50-50. What do you think I can do to convince you? Not to just ask you to believe me. You don't have to believe me. You have to see it. So what do you think one action I can do, and then pretty much eventually you will be convinced it's 50-50? Do the experiment a large number of times. I could do it 10 times, guys, and you'll see 7 heads and 3 tails. That gives you an impression probably the coin, just is loaded, or it's not a fair one. And probably it's not 50-50. But look, guys, eventually when you do an experiment a large number of times, it's going to balance out. So if I toss, just a coin 500 times, I can tell you guys, it's very likely you're going to see about 250 heads and 250 tails. And just to verify this, guys, I'm just going to show it to you, not just on the calculator. So if we go to the apps, probabilities, toss coins. Okay, let's toss. Okay, let's do it 10 times, guys. You see, you feel that there are more heads than tails. Let's do it more now. You see the balance now? 160, look. I got 82 and I got 79. Very close, just together. That should give you an impression that they're both going to happen the same number of times. So it is 50-50. And if you are still not convinced, you don't think it balances out, just keep doing the experiment. It will balance out eventually. And this is what we call the law of large numbers, guys. Now, there is another definition of probability. It's called subjective probability. It's based on intuition, intelligent guess. For example, a doctor may feel a patient has a 90% chance of full recovery. How does the doctor know it's 90%? It's just based on the experience of the doctor. He doesn't do the actual experiment to find out, what's the chance, just that the patient will recover. They're just from past experience. They just can make, just this statement. Weather forecasting, guys, it's usually an intelligent, educated guesses. When they say there is 90% chance of rain, and it's not always, I mean, sometimes they say 90% chance of rain, it doesn't rain. This is all subjective probability when you try to read, just into the future here. So a subjective probability, guys, is based on an intelligent or an educated guess. What I have here, I have 3 different probabilities. I'd like you guys to tell me which one is subjective, which one is classical, and which one is statistical or empirical probability. Classical is the definition, number of favorable outcomes divided by number of possible outcomes. Empirical or statistical probability is based on the table, a survey. We get results from a survey, just like here, that is called a statistical probability. And then the intelligent guess. What do you think of number 1, guys, is going to be? Which one of those? The probability that you will get the flu next year is 10%.
Subjective.
Yeah, that's subjective, based on the weather conditions and the viruses, etc. This is just a guess, guys. Can't do an experiment and find out whether the person is going to get it or not. The probability that a voter chosen at random will be younger than 35 years is 0.3. What do you think? Is it classical or statistical? How do we keep track of the ages of voters? It's through what? Surveys. We have information just like that in the table. So that will be, guys, a statistical probability or empirical. You see, chosen at random. So we're just doing a survey here. The probability of winning a 100 raffle tickets is 1 out of 100. So you have 100 tickets and one of them is winning, guys. That is a classical definition because it's 1 ticket in the favorable outcomes and 100 at the bottom in the denominator. So that will be classical. All right. And as I told you guys, the probability cannot exceed 1. We're almost. So let me just finish this. When the probability is 0, guys, then the event is impossible. And when the probability is 1, that means the event is certain to happen. Like the probability that today is Wednesday is 100%, is 1, because I know it's for sure Wednesday. Now, the last thing, guys, before we wrap this up. If I tell you the probability that it's going to rain today is 70%, I can ask you the following question. What's the probability that it's not going to rain today? So the probability that it will rain today is 70%, 0.7. What would it be the probability that it won't rain today?
30%.
Exactly. All probabilities, guys, add up to 100%. So this is not E. Just keep that formula in mind. Probability of E plus probability of not E, they add up to 1 always. Example. Probability of rain is 0.7. Then probability of no rain must be 0.3. Why? 1 minus 0.7 equals 0.3. So if you know the probability of an event, guys, you know what's the probability of the event doesn't happen always, because 2 probabilities must add up to 1. Okay, so I'm gonna stop here and we will continue tomorrow. I need another hour probably or so just to finish the chapter. It's not a long chapter, and then we'll do a review for the test.